Hello, welcome to session number 6 in the series Digital Circuit Design using VHDL. My name is Anurag Nigam, and somewhere I was discussing in session 5 I was discussing combinational circuits, and because of the time constraint I could not cover the entire thing. So I will continue from there on, and then by the end of this by the end of this session, I will introduce you to some sequential circuits. Okay, so let's get started. Let me just see if I'm recording. Yes, I am. So let's get started where we left from. So we have a package here where we have a half adder, full adder, and adder n bit, right? Now we are going to explore another simple circuit which is called multiplexer, right? So create a new design, and we will create a very simple 2:1 mux. So I will call this one as mux 2 to 1. Right, so this is a single bit 2 to 1 multiplexer. So let's see how this is going to be written. They're very small VHDL codes, so later on, you will encounter bigger and bigger codes. So I'm going to call this as mux 2 to 1, and here I'm going to have inputs as I0 and I1, and then outputs as Q, and there's another input actually, that is select line as 0, right? So we have I0, I1, and S0, right? And then we have got output Q. It's a combinational circuit. Okay, and here I'm just going to write this code. It's a very simple code. VHDL code for, there has to be a double dash, VHDL code for 2:1 mux single bit. Okay, I don't need to refer to anything other than IEEE library and std underscore logic underscore 1164 package, right? So here I have to write just single piece of single statement, which is going to be a conditional assignment. So I would say q is assigned I0 when S0 is equal to 0, else I1 when S0 equal to 1, else a default value of high impedance Z. So this is a capital Z. So with this I have defined a 2:1 mux. So this is very simple, and I am going to make a component out of it. So I'm just going to copy this and I'm going to paste it in the package, right? And that I am going to just change entity to component, and is optional, so I'm going to remove it, and end component. Okay, so this is a 2:1 single bit mux. Now if I want to do this 2:1 and bit mux, okay, so I can go here and I can create another another source, and here I will say create a file and call this as mux 2 to 1 n bit, right? And say okay. Again, the library is my circuits, and I'm going to say finish, and here I'm going to say mux 2 to 1 n bit. Okay, and here the inputs are going to be, again the width is going to be generic, so I'm going to start with I0 and I1, and they are of a width 7 down to 0, right? and then you have a select line which is a scalar, right? So this is a scalar line, and then output is also going to be n bit wide, so that will be Q, and this will be mode out, and again 7 down to 0, right? So once I'm done with this, the code is going to be as simple as that, as the 1 bit one, right? So why didn't it? Okay, so it is over here. This is n bit, correct? So just double click this one. So why is it stuck? Okay, so it opens here. Here I'm going to say VHDL code for 2:1 n bit multiplexer or mux. Okay, so here I don't want to do any structural programming. I will just write it down as a data flow, and so all I need to write is Q. So I'll introduce a generic here because I want to keep a variable width, so I will say generic, and n is an integer, and it has a default value, let's say 8, right? Okay, spelling mistake, fine. And then this I will make n minus 1 down to 0, and this one I will make n minus 1 down to 0, correct? And q is assigned I0 when S0 is equal to 0, right? Else I1 when S0 equal to 1. Else, now this is called aggregation, others, and each bit of the width, each bit of this word, which is width of n, is going to take a value of z, or high impedance. So this is a very simple declaration like this, and I'm showing you various ways to create this multiplexer. Now another example can be, let's say I want to do a 4:1 multiplexer, so which is n bit wide, right? So first of all I'm going to enter this as a component, right? Control C, and I'll enter this as a component in. Okay, so here indentation I will again adjust this one. Okay, generic and port, and this is going to be a component, and is optional, and n component. Okay, so this is done. So now I'm going to create a 4:1 mux, which is n bit wide. So add source, and I will go to create a file. So this is going to be a mux 4:1 n bit, and it will belong to the same library. Say finish. So I will call this as mux 4:1 n bit, and it has got 4 inputs, I0, I1, I2, and I3 of mode in, with a bus size of 8, and then I have a S0 and S1. Let's say S0, or rather S1 comma S0. Okay, this is mode in, this is a scalar. Okay, this is a scalar, Okay, and then you need a Q, which is a vector of the same width. Okay, so once I'm done with this is the one which shows up. So I'm going to show you some more constructs here. That's why I took this example. So this is a VHDL code for 4:1 max n bit, right? Okay, so over here I am going to do something called concatenation, but before that I'll introduce generic here, and that generic is going to be the width of the word, right, with a default value of 8. Okay, and this will be n minus 1 down to 0 and n minus 1 down to 0, right? And then I'm going to do a signal called select, which is a vector, which is a 2-bit vector. So std logic underscore vector, and this is going to be 1 down to 0. So this is 2-bit wide. And then here I am going to say select is assigned concatenation of s1 comma s0, correct? And then here I can use a selected assignment. So with cell select, okay, with cell select it can also be all single, so it is case insensitive. q is assigned q is assigned I0 when 0 0. So when select takes a value of 0 0, else I1, so there is no else here because I'm using a selected assignment. A selective assignment has a syntax which looks like this: I2 when 1 0 comma I3 when 1 1. Okay, and the last condition is others all values z when others. Okay, so okay, others. Okay, q by mistake is here in. Okay, so everything is corrected. So this is going to be a n bit wide 4:1 mux. So you can design any kind of a mux, but then the question comes is, what's the approach when the n, well, when 4:1, 8:1, 16:1, 32:1. So when this keeps on increasing, what's a good way of doing this? The good way of doing this is using something called tri-state buffers. Okay, so let's assume that each one of the inputs is going to drive a bus. Okay, and that bus is nothing but a std underscore logic underscore vector. Now the which one it is going to put onto that bus will be decided by a decoder and a output buffer, right? So we need to create a circuit which is called buffer. So I'll tell you what it means. So first of all, I'm going to take this one, convert it into a component inside the package, and this is a component. and this is optional and AND component. Okay, so this is a 4:1 mux which is n bit wide. Okay, uh, yeah, so we will go to something called output buffer. So what is output buffer? Output is same as the input when the buffer is enabled, else it stores its value. So it is going to use some form of a register, right? But internally what it does, we can see, we have to define is the functionality, right? So let's try to do a buffer uh, with the output enable. So I'm going to say create source, create a source, and this is Tristate buffer, try buffer, and this is going to be n bit wide, so I'm not going to put that. So this is a Tristate buffer. Library is my circuits, finish, and here in a Tristate buffer I have an n bit input. So let's say input is going to be A, or rather I is okay, and this is going to be, let's say, 7-bit wide. Then there's something called output enable. We can have this as active high, and that's going to be a scalar. And then I am going to have Q, which is a mode out of the same size as this one, and say okay. Okay, in a bus, if you want to put something, the output should have this tri-state buffer. So if the driver is talking to the bus, then the buffer is enabled. Otherwise, when it's disabled, it is high impedance. So that's the logic. So here I'll just open this one and say VHDL code for n bit tri-state buffer. Okay, okay, so all I'm going to do is, I am not going to say, I'm going to say when it is enabled, the input is communicated to the output. When it is disabled, then high impedance is uh, is going to the output. So very simple. So I can say Q is a sign. So let's make this generic first. So this is generic, and the width is n, and it's an integer with a default value of 8. So that's the generic definition. And then Q is assigned, so this will become n minus 1 down to 0, and this will become n minus 1 down to 0. Okay, so all I have to do is, I have to say Q is assigned I when OE is high. OE is high. Else it is going to be assigned others a high impedance tree. So this is a very simple, tri-state buffer. Okay, either the input is communicated to output if OE is high, or high impedance is communicated to the output. So this is like a output buffer or a tri-state buffer. So let's close some of these. Okay, so this tri-state buffer, I'll turn it into a component. And this will be called a component, and is this optional, and end of component. Okay, so now we have created a tri-state buffer, and we have uh, which is n bit wide, and we have OE as active high, right? Okay, so these are some of the buffers, some of the combinational circuits which will be used also in sequential circuits, right? So that's why I covered them. Now if I look at it, okay, I have designed these, okay, then I have designed multiplexers. Demultiplexers are not of much use right now, so that's why I'm not demonstrating that. Now let's do a decoder. So let's see how much time have we spent. Okay, 22 minutes. So let's do a n m bitwise byte decoder which has got n select lines, and the relationship between the input lines to output lines is output lines are 2 raised to n. So let's say n are the select lines, then the output lines are 2 raised to n, and whichever input is fed, okay, to these n lines or the address lines, okay, that line is going to go high or low, while the other lines are going to be in opposite state. So what I mean by that, I mean that if everything the output is 0, and if I give a select, okay, select address which is n bit wide, then that particular line is going to go high while all others are going to remain low. I can do the reverse of this also. Okay, all the output lines are going to be high while only the selected line is going to go low. Okay, so that is a decoder. So simple example is, let's say 3:8 decoder, right? So 8 I'm usually putting as a default value, but this is designed as generic, so it can be expanded to any word size, right? So let's do a n is to m decoder. Okay, so I'm going to go here and let's say add source, and I'm going to create a RTL source here, and here I'm going to say is decode n Ncrossm. Okay, so I'm doing a Ncrossm decoder. Again, the library is my circuits, and I'm going to say finish. Okay, so this I will call is DEC Ncrossm. So here I am going to have input lines which is going to be select line with a certain width which is n. Let's say this is 2 down to 0, and then I am going to have Q which is a out, which is going to be, okay, 2 raised to 3, 3 input lines, right? So it is going to be 8, so 7 down to 0. Okay, so we are done with this. Now I'll just write it out. It's very simple. Okay, I'm leaving it generic, so you can put any n or m. Only thing you have to take care is that m is 2 raised to n. Okay, so here it is. Okay, here I'm going to write VHDL code for Ncrossm decoder. Okay, and here I am going to make use of something called process. The selected assignment or any conditional assignment is not going to work here, because uh, somewhere you have to make all the lines except the one as 0. So you cannot have two assignments, concurrent assignments to the same bit. So I will as you go ahead, and you will know what I mean by that, right? And then that's why I have to use a process block, which is a concurrent block with a sensitivity list. But then the statement inside that block is going to be all sequential statements. Only simple assignments are allowed. Okay, conditional or selected assignments are not allowed. Somewhere Douglas Perry makes a mistake in one of its examples. Okay, so be careful when you read that. Only simple assignment statements are allowed inside the process block. Okay, selected assignment or conditional assignments inside the process block are not allowed. Okay, this is for a simple reason, because the statements have to have a nature of sequential nature, and selected assignment or conditional assignment is not sequential in nature. Okay, so let's do this. Okay, I'm going to use another package of IEEE, and that is called numeric underscore std.all. Okay, this will allow me to convert a std logic vector into an integer directly, and internally it is optimized because it is implementing something called mb merge. Okay, rtl underscore b merge. So this is a special rtl component which is created for this purpose. So it's not going to have a converter to convert a std logic vector into an integer. Internally there is something called b merge, and you can read about this in the manual. Okay, so let's do that. So over here, okay, inside this, all I have to do is I have to declare a process, process, and then I have to specify what it is sensitive to. So it is sensitive to select line. Okay, so we haven't created select yet, so let's create this. So this is a signal which is going to be select, called select, and then it is a std underscore logic underscore vector, and this is going to be, so I'm going to keep generic, right? So let's create two generics here. So I'm going to say generic, okay, and I'm going to say n is a integer, okay, with a default value of, let's say, 3, and then I have to put a semicolon and then say m is also a integer with a default value of 2 raised to 3, which is 8, and the last one will not have a semicolon, but after bracket you have to put a semicolon. So that's how I have declared two generics with default values of 3 and 8. So this one will become n minus 1, and this one will become m minus 1. Correct? So now I have to create select as std, so select as an integer. So okay, signal select as a std underscore logic. Do I need this? Answer is no, I don't need this. But then what the process will depend on? It has to depend on concurrency, so I have to create it. But then it can depend on s itself. I don't need select. Okay, so I can say here process dependent on S. So S is the only input, right? If there are more inputs, then there is certain issue. Okay, all the inputs which are going to be uh, the ones which affect the process block have to be specified inside its sensitivity list, which is over here. In this case, there is only one input S, so that's what I'm doing here. And then I would say begin, and then I would say end process. Okay, so that's how you write a process. And in a process, you see the keyword is process, so it's a concurrent statement on its own, and its sensitivity list is specified here as a comma separated list, and then this region is known as the declaration section. So I can declare a variable. Okay, so in this place you can declare a function, procedure, and a variable. You cannot declare a signal. Okay, so I can say variable, and I will call this as select, and I will call this as an integer. Correct? And then inside this I can write sequential statements. So I can say select is equal to, so in this case it will be assigned like this, not equal to. So variables are assigned with a colon followed by a equal to sign, and signals are assigned by a less than followed by equal to sign, right? So select is equal to integer, int, okay, to integer unsigned, and this is going to be S. Correct? So this will return me a integer value in select, and then I have to assign everything in Q. So simple assignment is allowed here, and I would say others, and it is assigned everything as 0. Okay, now I can take a specific value which is selected value of line, and that is assigned 1. Okay, so you see here that one of the bits of Q is assigned twice. This is not possible in a parallel construct or a concurrent construct. This twice assigning a signal twice is not allowed, because then you will have two drivers here. Okay, you will have two drivers for that bit. But in sequential, first time I'm assigning all the bits to 0, then I'm going to take the selected bit and assign a 1. So this is a double assignment for a bit, and this being a signal, it will create two drivers, right? And to avoid that, I have to put this inside a process block. So in that case, the simple assignment is treated like a assignment rather than as a driving or a driver. Okay, so once I'm done with this, okay, I'm going to check whether this decoder is going to work. So I'm going to set this decoder, okay, as a top level module, and then I'm going to go to settings and choose this for simulation as well as synthesis. So in general, it's already selected decode EX Ncrossm. In simulation, I'm going to select that. Okay, so I'll say okay. Now if I run the simulation, okay, is there any issue here? I don't think so. Okay, so spawn error. Okay, so I'm gonna close it. I'm gonna fix the error first. So what mistake I might have done? Let's try to fix this mistake. Spawn. Okay. What kind of error is that? So I'm using this numeric std all. I have an entity with a generic, and that looks okay. And then I have a port declaration that looks okay. Then I'm saying process is only dependent on s, correct? Okay, the spawn error occurs when there is a compilation issue. When the sequencing of the files which are compiled and not compiled, that kind of is affected, then it gives a spawn error. So all you have to do is do nothing but just repeat the run again. So I am going to go save everything and run simulation again. Okay, it's run, and I'm going to reset this. Okay, so here I am going to put in 0, force constant 0, and I'm going to simulate for 100 nanosecond. So the value is, the 0th bit is 1. Okay, so now I'm going to make this 1. Okay, run this again and save you all. So now the first bit has become 1, right? So as I change the select line, that output line is going to get 1 and the remaining lines are going to be 0. So let's make this one as 2, right? So I'm moving in the lower nibble. Okay, and save you all. So you see that the bit is passing on, and then I would force this to 3, right? So now it has reached a value of 8, right? So that's a value of 8, and then the next value is going to be 10, which is equivalent to 16. So this is a hex number, so it's not decimal 10, right? It is a hex 10, that is 16. So force a constant 4, so this will appear as 10, right? So the bit has shifted up, so this is the LSB for the higher nibble, and then it is 0 here. So this is working, right? And my interest is to show you what is internally done by the, so what is being internally done. So I'm going to close the simulation window, and I'm going to open the elaborate design. Say yes. This is a special component because this is very common. I could have written this using multiple, selected assignment, right? I could have done using selected assignment, or I could have done using conditional assignment also, checking the condition on S. But then I would be forced to use a fixed words I'm not willing to use. So this is the component which is called B merge, RTL B merge, and this is like uh, a mux. Okay, so this one bit is the one which is going to go to the selected bit, and all other bits are going to be 0. So this is going to be a mux. It will be a mux in lot of muxes uh, in parallel for each bit. So that's how it works. Okay, so you don't have to bother about the internals of how this decoder is constructed, but that's acting as a decoder and is efficient. Okay, so having done that, okay, I'm done with the combinational circuits. Now I'm going to use this decoder when I do a 7-segment display. Okay, so I'm going to use that. Okay, so now I'm going to show you some of the sequential circuits. So, well, there is nothing called sequential. Okay, so let me explain this. Okay, anything sequential is basically you are constructing out of combinational circuits which are not sequential, they are combinational, right? But then there is an element of delay, and by the time you feed back something as an input out from output to input, there is a delay and you lose the clock edge, so then that state is maintained until the next clock edge comes. So that's how your flip-flop works, right? So the simplest flip-flop is going to be a D flip-flop, right? So if you are not clear with these definitions of combinational circuit, sequential circuit, then there is a playlist for you, which is a digital circuit design using in CMOS, right? Using standard cells. So this is another playlist. There are 12 lectures. You can see those and then come back and then you'll understand all this. Okay, so anyways, I am going to create here flip-flops. So I'm going to add a source and let's say next and say create file, and I'm going to create a D flip-flop. The library is going to be my circuits, and then let's say finish. And what are the inputs of a D flip-flop? The inputs are D and clock. And what is the output? Q. Okay, now here when you talk about sequential circuits like flip-flops, you should be clear about the initial state. Okay, either you have a circuit where you fix the initial state by set or reset, okay, or okay, so that's one thing, or you would have to code in the initial state. So when you code in the initial state, okay, then uh, whatever you have coded, right, it's not efficient, right? So but still I want to show you simulation, so I'm going to show you that, right? But then anything you design, you should not build in the states, okay, initial states. You should rather have something like a preset and clear, right? So we haven't reached that state, okay? So if you want, we can code it with preset and clear also, right? So let's make a let's go here with a D flip-flop. So if you don't want to code the state, initial state, you will have to put in a means to either preset or clear. So I'm going to put clear in here. So VHDL code for D flip-flop with clear. Okay, sometimes there is a difference between preset and clear. Okay, the difference is preset is going to be synchronous, right? Synchronous, while clear is going to be asynchronous, right? So if there is a clock, then irrespective of the clock status, if you put in a clear, it's going to clear it. So this is asynchronous, right? So I am going to have a D flip-flop with clear, okay, and then this is a negative edge triggered, negative edge triggered D flip-flop clear. Okay, I'm going to delete all this stuff, and this is very simple. I'm going to insert a clear also here, right? And I am going to write, I'm going to create a signal here, and that signal is an intermediate signal. Now in flip-flops, as I told you, there is going to be feedback, and if you have an output feeding back in, then the output has to be declared as an in-out or as a buffer. But still, if you want to declare output pin as an output pin only, not as an in-out pin, you have to have a wire, okay, which is bidirectional. So I'm creating signal W as an intermediate output, and this is of the type std underscore logic, right? I could have given an initial value. I am not, because clear is going to do that. So I would say W is assigned D when W is assigned D when clock has an event. So this is called an attribute which returns a boolean, and clock became 0, which means that this was a falling edge. Else it is assigned 0 when, okay, so the first condition to be checked is 0. Okay, so I don't want this to be a second condition, so I'm going to I'm going to exchange it. So is assigned 0 when clear equal to 1. So irrespective of what clock is doing, W is going to go 0 when clear equal to 1, else D when clock has an event and clock became 0. Clock became 0. And I will add a condition that clear is low. So when clear is low, I am passing D, and when the clock edge comes in, I'm passing D to W. When clear is high, then it's going to be assigned 0. Okay, so this is I just don't want to create side effects, that's why I'm putting that there. Else W is assigned W itself. So this has become a register file with a clear, and then at the end I can say Q is assigned W. Okay, so this one is a D flip-flop, right, where I can clear this. So do I want to check this? No, I won't check it. I will check a T flip-flop. Okay, so this one I am going to make a component out of it. Right, and then this is optional, and AND component, and here that's the component declaration for D flip-flop. Now I am going to make a T flip-flop out of this D flip-flop, right? So how do I go about doing that? Okay, I am going to create another design, and I would say create a file. I'll call this as T flip flop, and I'll put it in the same library and say finish. And this one is going to have inputs as T comma clock comma clear, right? I think that's the sequence also for D, right? And then it is going to have Q as the output. Okay, so that's the T flip-flop, and I'm going to say VHDL code for T flip-flop. Okay, so here I'm going to put here library my circuits, and then package my circuits.circuits.r. So I'll see if there is a problem here. Okay, so this is done. Then I am going to say create a signal here which is D, and this is std underscore logic. So this is a wire. Okay, and I am also going to have a W. Do I need a W? I need to do a feedback, so I need a W. Okay, so I am going to say I'm going to instantiate. Before I instantiate, I'm going to declare D. D is assigned W XOR with T, correct? And then I'm going to instantiate a DF1 as a D flip-flop, right? And then I have a port map. Okay, and that port map goes like this. First input is a D. Okay, second input is going to be a clock, which is going to be the global clock for this design, and clear, which is a global clear for the design. And then there is going to be a Q, which in this case is going to be a W. Okay, so this is D flip-flop, and finally I would say Q is assigned W. Okay, so I have declared a T flip-flop using a D flip-flop, right? So I'm going to save it, and I'm going to run the simulation to see if it is behaving as it is supposed to behave, right? So first of all, I am going to set this as a top level design, T flip-flop, and then my generic is also going to be a simulation is going to be a T flip-flop. Say apply. So both are T flip-flops, and when I do that, it should show up as a top level module, right? So I say run simulation. Now while running, you have to be careful. First you have to set or clear the flip-flop, because unless you have an initial state, the flip-flop is not going to toggle, right? Okay, so I am going to first reset it, and here I am going to make toggle as 0. So if I make toggle as 0, it's not going to toggle, right? Okay, okay, so I am going to force this constant toggle as 0. Then I am going to say that the clock is going to force as a clock with a period of 100 nanosecond with a width of of 50% duty cycle, leading edge is 1, trailing edge is 0, and say okay. So that's a clock, and this clear I am going to set as 1 because I have to first clear the flip-flop, and I'll simulate this one. So I do not want to see D and W, so I'm going to delete that. I just want to see Q and say run. So now the initial state is set to 0, right? So the initial state, because the clear has come as 1, so the initial state is set to 0. Now I'm going to make clear as 0. Sorry, I'm going to make clear as 0. So now the D flip-flop is going to maintain that state, right? And the clock is not going to toggle unless T goes 1. So I simulate once more and say view all. So here what I have done, I have set the clear out now. Now I am going to turn on the toggle. So I'm going to force this to 1, and then I am going to simulate this for 5 cycles. Okay, so that's why 500 nanosecond, and say run. So when I do this and say we'll view all, you see at this point on the falling edge, the output starts toggling on each falling edge, right? And then I can take the toggle to be to 0. This will force the state to be high because it's the state is high. For the next 500 seconds it has maintained the state because the toggle has gone low, right? Now I turn the toggle back up again, 1, and run this again. So now it's toggling again, right? I can toggle it more. So you see, as long as I have T as high, it will keep on toggling. One more. Okay, so you see that this is a divide by 2, right? So this is a T flip-flop. So let's see how much time have I spent on this. So I'm close to 1 hour, so I'm going to stop here. Okay, and before I stop, I'm going to conclude some things over here. So I have shown you half adder, full adder, n-bit adder, multiplexer, decoder. I haven't shown you demultiplexer, but it's not of much use. So I have shown up to decoder. Then I went to sequential circuit. I've shown you D flip-flop and a T flip-flop, right? And then I'm going to make circuits out of this. Okay, so I'm going to stop here. Thanks a lot. Thank you.